Our speaker tonight is David Grier, who's the editor of the preeminent journal of computer history, the IEEE Annals of the History of Computing. And he's an associate professor of science and technology policy at George Washington University. He claims to be, and I have no reason to disbelieve it, a third-generation computer scientist, even though that's relatively rare in our business. He worked on the design team for the Burroughs scientific processor in the 1980s. His father, Thomas Grier, joined UNIVAC in the 1950s and then was an employee of Burroughs after that. And his grandmother, Blanche O'Kane, was trained as a human computer, as some of the people we have here tonight, at the University of Michigan in the 1920s. David holds a bachelor's degree in mathematics from Middlebury College and a PhD in statistics from the University of Washington. He now writes extensively on the social aspects of computers, of which human computers are certainly an example. Please welcome tonight Professor David Grier.
Well, thank you for such a wonderful and warm introduction, and I feel humbled to be part of such distinguished company in the speaker series. I've had just an absolutely wonderful afternoon here talking with a couple human computers myself. And I just feel that it sort of enriched me to get to know them a little bit better and to understand what they did. And because of that, and because we have several in the audience tonight, I thought that I would particularly like to talk about computing, the act of doing scientific calculations by hand. If you ever want an opportunity to kill conversation at a dinner party, announce loudly that you are working on a book in which long division plays a prominent role. You'd just be amazed what people will do to you at that point. I'd like to talk about computing as a woman's profession, because by and large, it was not. We have come to an understanding, a myth, that said computers were women that did the work of computers before we had computers. But that does not look very feminine to me. A very prominent 19th century computer named Charles Henry Davis. You can see some women in here. This is World War I. This is a group of the ballistic computers, the people who did trajectories of long-range guns. And there are several women in there. They're standing in front of Bartholdi Fountain in front of Washington, D.C.'s Capitol. But you see a good number of men there. Another World War I group. This is with the Food Administration, the rationing group largely for America's food production. And you notice that all of these people seem to be by and large in coats and ties. Iowa State University, 1927. Okay, there are some women, but you notice 3 guys sitting right there. And finally, before finally, L.J. Comrie, who is perhaps the most important human computer of the 20th century, very definitely male. And finally, my favorite group. This is a Depression-era computing group, perhaps the largest computing group of the 20th century. 450 people doing calculations with nothing but paper and pencil. It was 17% female, 83% male. So in knowing this fact, and knowing the fact that perhaps over the course of history, the bulk of people who've done calculations have been male, what do we learn from, and particularly what do we do when we see women starting to enter the field and starting looking at the position they held during World War II and in the years that followed? One of the things we need to understand and start at is that computing is really the career of the dispossessed, of those people who lacked societal, monetary, family connections that would allow them to take a career in the sciences. Women, by the end, certainly were a very large cohort, and perhaps the largest during the 40s and 50s. But it was men, it was blacks, Irish, Jews. The handicapped during the 30s, a large number of them had polio. And the merely poor. And when you start looking at how these things evolved and how they go forth, you begin to see that they may not have been the ones that built the electronic computers, but they certainly laid the foundation for it and began to show what work could be done by machines, what could be automated, and what could be, and what required, at least in their time, human intervention. Now, I started this story, and I started this book in part because of my grandmother, the story that was mentioned earlier. I had a dinner with my grandmother now almost 20 years ago, and we were gossiping about my cousins. And if you have cousins like my cousins, you have plenty to gossip about. And we were going on about this one cousin who was on her 4th or 5th husband, I am not sure at the time. It's 5 now. And as we were talking, in the middle of it, she stopped, stared at me cold, and said, you know, I've always regretted that I've never used my calculus. And then went right on going. How many of you have had a grandmother experience like that? I do not see lots of hands up. There should be more. I let it go, and I don't know why I let it go. And you may think that this book is penance for not saying it, for not asking then. But be that as it may. She passed away not long thereafter, and I asked my mom what she knew about it, and she looked at me as if I had lost my mind. She said, I don't know, talk to my brother. So I called up my uncle and said, you know, Uncle Charles, what do you know? This is what my grandmother said. And she paused in kind of the reflexive way he gets. Said she wasn't very well at the end. She took bookkeeping classes to help with the gas station. My people are gas station people. Your people may be others, but that is kind of my ethnic group. If you live in Washtenaw County or have purchased gasoline in Washtenaw County, you have purchased gasoline from some cousin of mine. There are a few that have mini marts, and there's Cousin Julie who owns a car wash. But we are gas station people in Ann Arbor, Michigan. I called up my cousin. He suggested I call crazy cousin Janice, who is the family genealogist. And in talking with her, I got the whole story. I got the Irish immigration, I got Ellis Island, I got the sea, the wine dark sea, and all these things. And finally she ended up by saying dearie, which she uses about every other sentence. Dearie, she says, dearie. Your great-grandfather, your grandmother's father, when he worked, which was not often because he was mostly drunk, he was a handyman. His wife, your great-grandmother, cleaned hotel rooms. Your grandmother didn't go to college. She didn't take calculus. So I, still feeling bothered by this, I called up the University of Michigan. Why not? Ann Arbor. Let's just roll it. The most thing they can do is laugh at me. I say, hi, I'm a professor. I'd like to know if my grandmother attended your school, and could I see her transcript? And they said yes with remarkable speed, which makes you wonder about your grandchildren. You may want to have them sign non-disclosures. And they came back very quickly and said, we have a transcript for a woman with the name of your grandmother. And I said, when did she graduate? And they said, 21. And I go, yes, that's right. Mom's born in 24. This is it. This is the woman. What did she major in? And you hear this flipping of paper. Oh, here it is. Mathematics. There were 12 mathematics graduates in 1921 at the University of Michigan. Approximately the exact same number they had last year. 6 of them were women. 5 of them had careers in mathematics. 1 ran a census office in New Orleans. 1 was an actuary in New York City, owned her own business, got herself bought out in the 50s, and became fairly well-to-do and donated a bunch of money back to the university. 1 did load calculations for Detroit Edison. 1 led the Department of Health Statistics for the state of Michigan. 1 was an editor for the Chemical Rubber Company, the people that do those big fat handbooks of numbers. And then there was a woman who kept books for a gas station in downtown Ann Arbor. That led me to a question. Who are the other 5 women? What did they do? Why did they get involved? What was the world that they inhabited? What did they hope to get out of it? What did they hope to accomplish? And as I started spinning the story out, it kept getting bigger and bigger. And it led to where I have decided all true stories begin, to Halley's Comet. All stories of science begin with Halley's Comet. If it's before Halley's Comet, I really don't care. Halley's Comet, as I began working with the story, became really the metronome, the thing that beat out the rhythm of the story. Allowed me to avoid writing an and-then book. I edit a journal, and I have a great deal of challenge getting people to stop writing and-then articles, which is, and then this happened, and then that happened, and then something else happened. And then following that, another thing happened. You need a story. You need a development. You need some drama. You need some focus. And Halley's Comet provided that, and it also, as far as I could tell, provided the honest starting point. Now, we know Halley's Comet is this. This is taken in the recent return. We know it's important. We know that it was discovered by Edmund Halley. And usually people's knowledge ends there. It's the first known periodic comet. Most people don't know that most comets are not periodic. They just come zipping by and then they're gone. It's a long-term periodic comet. Most comets have a much shorter period than Halley's. And what they don't know is that it was the first real major test of Newton's theory of gravitation. When Newton developed it, and if you remember your history, I understand this may have slipped thought, Halley is kind of Newton's editor. He helped Newton organize his thought, otherwise Principia Mathematica would have been a pile of notes that would be referred to as this wonderful document, but no one ever cited, no one ever finished. He helped Newton get it in form, he introduced him to the Royal Society, he got it out. He got one of the major pieces of Western civilization finished. And he learned calculus in doing it. He had some comet observations, and in 1695 he sat down with them to see if he could fit them to orbits. And he was particularly interested in one that he had seen, this one, Halleys Comet, in 1682, because he was pretty sure that it was periodic. It seemed to have the same orbital parameters, come from the same direction of the sky as two other sightings, one by Kepler about 75 years before, and one by Appian about 77 years before that. And in doing that, he was pretty sure it was going to come back again, but he could not handle the calculations. He knew that there was a difference in orbital periods, that it wasn't just a nice thing going around, and he was pretty sure that the problem lay in Saturn and Jupiter. There's a lot of gravity there. There's a great deal of pull to deform the orbit of a comet. He had no idea how to do it. He asked Newton. Newton kind of shrugged his shoulders and said, "It's not my problem anymore. I've got this great job at the Mint, and I'm not really interested." And so Halley wrote a note that basically says, "I think it's coming back in 1757 or 8 or 9 and maybe 60. I'm not entirely sure. I will leave that to posterity to decide." The thing about Newton's work with the planets is that the planets are more or less visible. And when things are visible, when data is there in front of you, the temptation to cut corners is high, to make your equations fit your observations. Halley's Comet is invisible for almost all of its orbit. So you either get it right or you don't. And your calculations are on faith. No one was really interested in doing it. In fact, some authors thought this was such a hoot that they made outrageous fun of it. Gulliver's Travels. We all read the little thing about the Lilliputians, the little teeny people. We forget the thing about the Laputans, the scientists who are mad. They're mad in some ways is because they're scared of a comet that's going to come back in 1757, 1758, 1759, or thereabouts. And they think they can calculate it, but they're wrong. That was Jonathan Swift's way of mocking it. No one really took up the cause. Whoops, that's the first sighting of it. The sighting is 1682. The people who took up the cause were three astronomers in France. The English were too touchy about this. The one up in your upper left is Alexis Clairaut. He provided the mathematics. Over here is Joseph Lalande, who was then a young astronomer who was going to be, who was known, he became Astronomer Royal of the Paris Observatory. He was known at the time as the most supremely ugly man in Paris. And in the middle is Renée Lepaute. She comes from the thin strata of very wealthy bourgeoisie. Her husband was a clockmaker. Everyone else in Paris at that time was either aristocrats, clergy, or peasants waiting to revolt about 40 years later. It may have been Lepaute's idea. Lalande suggests that it was. And what they did is they set out to compute the orbit of Halley's Comet to figure out when it was going to come back. They were going to compute the perihelion, the point when it's closest to the sun. It was such a big problem that they didn't know how to start, but they recognized they could divide the labor, that it didn't need to be all Clairaut's doing, that Lepaute and Lalande would work on the problems of Jupiter and Saturn, and Clairaut would deal with the comet itself. And once they did that, they write this wonderful story of sitting in the Palais d'Orléans wearing the court dress of the time, the knee breeches for the guys. The woman has about 8 petticoats. Lepaute has about 8 petticoats. They're beauty marks. There's white wigs. There's servants rushing around feeding them. And they are working with quill pens, scribbling away, computing the orbit of Halley's Comet. Now, when you do this, you want to be sure you've got it right. So they ended up computing 3 orbits, Appian's to Kepler's, Kepler's to Halley's, and then they jumped off and tried to figure out when it was going to end. They worked about 3 months on the project. Lalande, who left the best account, is a bit of a crybaby. He complained that in the process he developed a mathematically related ailment that would stalk him for the rest of his days. They finish in November. They announce that they have got a date that Halley's Comet is going to get its closest approach to the sun, April 15th, give or take 30 days. Comet is seen in the skies in January. They do some revised orbital calculations, and they realize that its closest approach to the sun will be March 15th, a month with 31 days. Needless to say, there's a big fight ensues after this. A number of people, including many of the French philosophers, say they were lucky. And modern research has said that they were, to some extent, part because they didn't know about two planets, Neptune and Uranus. The fight goes on. Is mathematics real? Is calculation important? Can you use large-scale calculation in the work of science? And as part of that, the question is, can people who are not the scientist, who are not that person, the mathematician, can they do work that is part of the scientific method? They finally kind of just all stare at each other and say, let's disagree and call it quits. But this is where it begins. And it starts unfolding from there, the divided labor of computation, where you can give work to people who are not the ones doing the original analysis. On the right, we have Babbage, who proves to be very important in this work. On the left is Gaspard de Prunay, the French engineer, who really came up with the basic structure that all computing groups after him ever had. The structure here has a scientist at the top who defines it, a group of people who do the calculations, who at some level, as Babbage points out in his writings, can be the cheapest people you can afford. And in the middle is something that takes a while that people understand. It's an occupation known as the planner, the person who takes the equation from the scientist and puts it in forms that the computer can work on. De Prunay's problem involved the metric system. The metric system came out of the French Revolution, and it was designed to solve a political problem. France at that point had 3 major systems of measurements and several dozen minor ones, and people were exploiting them shamelessly for their own profit. The Revolution wanted to systematize it, pull it in, remove some of that political structure, and as a last minute, they said to themselves, oh yeah, we want the standards to be outside of political control. We want them centralized. We want them all to be related to each other, a length to area to volume to weight. And oh yeah, we want it decimal. That was kind of a last minute thought. And if we're going to do weight and volume and all that, let's also do time, and let's also do angle measure. Instead of having a 90 degree, a right angle with 90 degrees, they would have one with 100 grads. They thought that was a good idea. Well, that's fine, and it's pretty easy to make protractors with 100 grads, 100 subdivisions. But you can't really, no one would care about using it unless you had trig tables. Because trig was, angle measures, the big users of it were navigators and surveyors, and they were using trig to compute the area of land and the location of points on the globe. And no one, no matter how good a revolutionary, is going to take an angle measure in grads, convert it to degrees, use a trig table, and then convert it back. So he took the task and he developed a computing group that involved 90 computers who were largely personal servants laid off by the revolution. A planner, there was a group of his friends, and he and a group of mathematicians, largely from the newly forming École de Polytechnique, were the scientists. Babbage saw this and said, this is the structure. He, of course, was interested in replacing the computers with machines. But this structure remained the structure for the next 2.5 centuries. Now, one of the things you learn about computers is that it was done in observatories. And that is sort of true. But the big place that it developed was in almanacs, because almanacs were a product. They had to come out year by year. The British started developing theirs in 1767, even before the French Revolution. And it's through Babbage's contact with the almanac that he comes up with the idea for his 2 major machines, his difference engine and his analytical engine. In the United States, the person who organizes the almanac is Charles Henry Davis, whose picture we've seen before. And one of his computers, his only female computer, is Mariah Mitchell. Mariah Mitchell is recruited because she's a friend of the Davis family. Her father is a banker on Nantucket, an amateur astronomer, and part of America's very small scientific circle. She has a position that we see for a while in the role of women in computation. The first women who get involved are either wives or daughters of people who have standing in the scientific community. The example of how it worked for Mariah Mitchell, and this is to say nothing about their talent. That was the hook they needed. In 1848, Mariah Mitchell discovers a comet. Fairly common thing. It was not an important comet. It went through, it's gone, it's non-periodic. Her father said, this is cool. We should tell the Harvard Observatory about it, and we should notify the observatories in Europe. And she says, no, I don't think I should do that. Well, he's not about to let her be retiring. He sends off letters saying, my daughter's discovered a comet. Is it unique? Is she to be identified as the discoverer? The Harvard Observatory, which had found very little new by that point, thinks this is a great idea and starts a full press campaign to get her recognized as the discoverer of it. There were a couple of European observers who saw it at about the same time. The person who does the recognizing happens to be an amateur astronomer, the King of Denmark, and the ambassador to Denmark happens to be a Harvard alum. And they do a full court press to make sure that Mariah Mitchell's comet is known as Mariah Mitchell's comet. And it was trumpeted as a major scientific discovery. This is to take nothing away from her accomplishments. She was a very skilled astronomer, certainly better than almost all of the men that she knew. She ends up becoming a professor at Vassar. But she spent 10 years as a computer because in doing computation, they wanted men of good training and good breeding. And she was not a man, but she was of good training and good breeding. And that her connection with her father and through Charles Henry Davis brought her in. There are, in her age, no public women figures. The major start of the women's movement, which we usually date to the Seneca Falls Conference on the Rights of Women, occurs the exact same year that she is finding her comet. So, in effect, there needs to be a standing, and it is through those men that help provide it. It takes 30 years before women begin to enter it in science in large numbers. And the place that they do in computing is at the Harvard Observatory. And this is a picture of the Harvard Observatory computing room. Again, the first round tends to be wives and mothers. But this is the time when women are moving into offices in big numbers. When women are starting to become clerks, and particularly stenographers. When typewriters are starting to enter, and they're becoming typewriter operators, as they originally called. The Harvard Observatory had a huge backlog of data. They did not know how to reduce it, how to put it in form that could be used for research. And in particular, in 1875, the head of the observatory, Edward Pickering, was approached by a couple relatives, female relatives, of former Harvard observers, and asked if they could do some of the work because they needed to find a job to support their families. Pickering thought this was great and brought them in. Now, Pickering, after starting this, begins hiring more, and this computing room is well known as an early training ground for women scientists. There's a little bit of a downside to it. He is thought of as liberal, as forward-thinking. One of his patrons was a woman who helped support this. His public letters have become sort of a model and are often quoted about how women are specially suited to computing. They are detail-oriented, they are dedicated, they are not easily distressed. It's the right job for a woman. His private letters are straightforward and blunt. We can pay them 20% of what we pay men. The Naval Observatory in Washington, the big competitor of the Harvard Observatory, is livid about this. How can we do the same quality work if we have to pay 5 times the salaries? There is a wonderful document, which is in my book, which I have promised, I've made a certain promise to my wife, but she's not here. One of the observers in 1779, 1780, did a wonderful little document that describes life in the Harvard Observatory. It is a parody of the Gilbert and Sullivan play, the HMS Pinafore, which premiered that year in Boston and also in London. He went to it, he got the script, and as many people have before and since, he rewrote it in his own local environment. And it starts with a bunch of computers, and my promise is that I will not sing this in public when my wife is president. But, you know, the HMS Pinafore starts with sailors singing, "We sail the ocean blue, and our salty ship's a beauty," and so forth and so on. This starts with a chorus of female computers. "We compute the starry night, and our record book's a beauty." And it goes on from there. Now, those of you who are HMS Pinafore fans, and I heard some stickers, so I know that there are some of you who listen to it, you know, maybe when the bathroom is closed and you put it on your little MP3 player and no one knows. The basic plots of all of them are the same. A young man falls in love with a young woman who are socially ill-suited to wed. Then follows 2.5 acts of a ponderous baritone, lengthy dances, several choruses, and several inexplicable songs that no one really knows what's going on. About 15 minutes to the end, a miracle occurs. And somehow the young man and woman can wed, there's a dance, a chorus, and a patriotic song, and the thing's over. In this case, the young sailor and his captain were switched at birth, and there are all sorts of generational problems, but it worked and was very popular in its day. And the guy who rewrote it for the Harvard Observatory could have done the exact same thing. You know, the observer, the male, is from Beacon Hill and Harvard graduate, and the woman is from the high school, the newly formed Cambridge Girls' School. And there are objections because it's Boston, blue bloods, all that. Many things occur, and the woman proves to be a foundling who was abandoned as a child by a very wealthy financier. He didn't do that. It's not a parody about a boy in love with a girl. It's about a boy in love with his science, in particular with his telescope. There's some Freudian imagery here I don't like. But let's leave that aside. He starts going, and then step by step the women vanish, until all that's left is a boy singing about his telescope. He is not such a fool, however, as to give the Lovers Lament to a male voice, or even worse, to a telescope. Imagine how that would sound. He gives it to the only identified woman, Rhoda Saunders, who is the name of a real computer in the Harvard Observatory. She may have had the best voice. She may have become his wife. I'm not entirely clear on that. Or she may have just been the best personality. She sings the Lover's Lament. Sorry her lot, who adds too well. Dull is the mind that computes but vainly. It's actually a fairly decent piece of writing, because it says, hi, we work during the days, the boys get to come in at night, and we have to go home. We can't use the equipment. We don't get to do any of the fun stuff. We just sit and compute. Heavy the heart that bows the head, goes the chorus, when the fingers are tender and the ink is red. Red ink was what they used to correct mistakes in calculation. And in some way, that describes the fall, or the start of the fall. With the Harvard Observatory, we start looking to replace the computers, the people who work at this level, with people that we can hire as cheaply as possible and get as much skill as we can. In the coming years, in the later part of the century, we see a few people. These are English. Karl Pearson, with his Brunsviga contemplating a bust of Galton. And Edmund Whittaker, the mathematician. These form some of the early computing labs in their own right. Whittaker does a book, Whittaker and Watson, that becomes a stable of applied mathematics. Karl Pearson, founder of modern statistics. They both start hiring women with that eye that they can get people from the women's colleges and bring them into their office and do the work. Pearson is a wonderful man. There's a new biography of him. He is a brilliant visionary, a stunning mathematician, a hypocrite, and he knows it. He knows that he's paying these people less than he ought, but he can get away with it, and so he does it. He's a Fabian socialist. George Bernard Shaw is a friend of his. He tries to give a wedding present to George Bernard Shaw, of all things. And he knows that he can exploit the women to get his work done, and it's a choice that bothers him, but he makes it nonetheless. Karl Pearson, interestingly enough, there's a play that George Bernard Shaw does called Mrs. Warren's Profession. For those of you who are Shavians, you know darn well what Mrs. Warren's profession is. It is a profession of ill repute, a profession that is often identified as the oldest profession of women. What we often don't know is that the main character in the play is Mrs. Warren's daughter, a woman called Vivian Warren. And we don't know quite what she does, or we don't remember. She is, in fact, a human computer. And Shaw uses it. Pearson viewed the original manuscript as a way for women to sort of find a sphere of their own, to break out and have a world in which they can be in charge and men won't butt in. This is part of the second theme that is coming even at this point, that this is not only suitable for women, it is women's work. Men should keep out of it. It continues later on, although it's broken from time to time. This is World War I. And the big thing in World War I are these very large guns. This is a railroad cannon. One of the few American guns that made to France can shoot shells about 25 miles. It was not quite the first war. The Boer War really is, where you're firing shells at things you can't see. In the United States, and to do that, you need ballistic tables. You need tables that track out the flight of the shells. It is also the first war with airplanes, and to shoot them down, you need a different set of ballistic tables that are actually much harder to compute and tended to be the ones done by hand. This is Oswald Veblen, the Princeton mathematician. This is Elizabeth Webb Wilson, his chief computer. She has a bachelor's degree in mathematics, has won the mathematics prize in her university. And in 1917, when she graduated, her entire male peers volunteered for the Army. She graduated in a class of about 165 men joined the Army. Oddly enough, all the women volunteered too, and they wouldn't take them. They were told to go back and roll bandages. 1917 is also the year of women's suffrage. It is the year that the White House is under 24-hour picket. It is when the Capitol is being constantly barraged by marches, by people chanting. There's a hunger strike in one of the Washington prisons, and she lives across the street from the Capitol. She watches it and decides not to roll bandages. When the government opens jobs for women in offices, she runs and signs up. They say, you can be a clerk. She says, no, I'm a mathematician. She has to say this 9 times. She declines 8 jobs and ends up being Oswald Veblen's computing assistant and does much of the work for the calculations that he needs for directing guns. Veblen and his peers at the end of the war felt that they had done service, and their service was largely about 3 months at length, the summer of 1918, that they deserved to be rewarded. And in many ways they were. Princeton University got federal funds that we weren't really seen again until World War II. Most of the people who worked with him who were male mathematicians got jobs in good universities. Elizabeth Webb Wilson was waiting for the same thing. She ended up teaching at Washington Central High School for 6 years. Step by step and piece by piece, she pulls her way back up, ends up getting a PhD from Radcliffe in the late 30s, and becomes kind of a gadfly on insurance and actuarial issues in her time. And in the 40s, actually, has an apartment near Harvard and is kind of the social director for American mathematics. But it's a world in which she hoped that it was going to pay her back, and never quite did. During the 20s and 30s, we start seeing a professionalization of computing. This is a Brown mathematician, R.C. Archibald. He starts printing a magazine, Math Tables and Other Aids to Computation, which becomes the scholarly journal for computers. They have methods, they have discussion of tables, which are the major computing aid. They talk about how things are to be done, and it is really the place where computing is discussed. But again, we start seeing a clear dividing line. There's a group of men who run this, and a group of women who do most of the work. This pairing right here represents, in my mind, sort of the height of the computing. The stuff I discussed today with the computers who worked at Ames, I learned a lot because I didn't do much with the aeronautical group. This is the Math Tables project. This is a WPA project. It took 450 homeless people off the streets of New York and put them to work doing tables, trig tables, cosine tables, Bessel function tables, differential equations. They occupied a whole floor of an old industrial building in New York City, not all that far from where the bus terminal is. And this was in the 30s, and it was a lot scuzzier then. The leaders were 2, Arnold Lowen and Gertrude Blanche. Arnold Lowen, PhD physics from Columbia, Gertrude Blanche, PhD mathematics from Cornell. When the WPA announced that they were setting it up, they had one thing in mind. They were doing it in the winter of 1937-38. If you're familiar with the WPA, they built parks. They did things in the public good. They built 1,000 auditoriums. They built airports. They built roads. And the classic pictures you see are a bunch of laborers holding shovels together, grading a road. And you say, boy, times were tough. And it doesn't dawn on you that they had road graders in 1930s. just that the WPA wouldn't pay for them. They wanted to hire as many people as possible. In 1937 and 1938, they needed more jobs, and particularly they needed winter jobs. And someone had a great idea. Let's put together a computing group. They followed the classic model. There was a few scientists at the top. There's a group of planners, which Gertrude Blanche led that group. And there were 450 people who were out unemployed workers. And as unemployed workers, they were pretty much the people they could pay the absolute least to, 20 cents an hour. The bulk of them were Jewish or Irish, about 20% black, 17% female. Awful lot of polio victims were involved, a number of people who had epilepsy. The stories of the first days were amazing, but the WPA really didn't care. They were off the street. They seemed to be doing useful work. What you get out of her story, out of Gertrude Blanche, is to me just an interesting thing. She had graduated from high school in 1913, and her father had died within weeks of her graduation. She had worked for 15 years to support her family, and then her mother had died, and that had freed her to go to college. She had entered college at the age of 32, finished in 3.5 years, Phi Beta Kappa, magna cum laude, physics and mathematics at NYU. Gets into Cornell, gets a scholarship, completes her PhD with Virgil Snyder, a former president of the American Math Society. And there's the old statement, math is a young man's game. By the time you're out of your 20s, you're washed up. By the time you're 40s, you should be retired. She got her degree just before her 40th birthday. It was the depth of the Depression. She was a woman. She was Jewish. What more do you need to have against you? She got a job working in an office in Manhattan. 23rd Street, they made cameras. She liked it. There were carpets on the floor. Wainscoting, that seemed to be important. Wainscoting on the walls. She had a door. When the WPA learned about her, they just fell over backwards. They had tried to get full-scale mathematicians, but they had gotten none. They'd asked Oswald Veblen, he turned up his nose. They'd asked Columbia to sponsor it. They were not about to touch it. When they found her, they were very excited to hear what she had to say. Would she do it? Would she take the job of leading the group? They took her to the building, an old industrial building, 33rd Street and 11th Avenue. I've been in it. I hope it was better then. They went up to the 7th floor, open industrial elevator. Dust, she described, was everywhere. The windows were just streaked with dirt. She looked around. All the furniture she saw was this piled mess in the back that was all broken down. They were told there was no money for adding machines at the start. She looked around and she said, this is it. If I don't take this, I will never be a scientist. And she decided to risk it. She went back and resigned. The WPA hoped this group would last for 2 or 3 years. It lasted for a decade. It outlasted the WPA. It became the largest computing group of the Office of Scientific Research and Development. She in particular, Gertrude Blanche, was particularly good about hiring women to be in the leadership class and to bringing those who were in the computing tables up into it. They had training classes for these people and moved them through step by step. For 1 year, she got the mathematician Cornelius Lanchos to be there as kind of a mathematical guru and guide. And that's the main picture. The picture I just find oddly mind-boggling. Just 450 people stretched out doing calculation. The two people that are best known, and many of you in here know these two people, are Irene Stegan and Milton Abramovitz. They're the editors of what is called by a number of names. AMS 55, you may know it by, Handbook of Math Functions, or just Abramovitz and Stegan. It's a book about that thick of how to compute almost anything you need to know. Milton Abramovitz was Gertrude Blanche's lieutenant. He was sort of the staff sergeant that kept the computers in line. Irene Stegan was a Catholic school math teacher. She had been laid off because the diocese was losing money. And Gertrude Blanche hired both of the two of them. In 1948, after it's all over, after the war is over and their money has run out, a good group of this organization got pulled into the Bureau of Standards, including Stegan and Abramovitz. They immediately planned to do a compendium handbook for computing because several individuals, notably MIT professor Phil Morris, said, you know, computers aren't going to solve all our problems immediately. And he complained that he, a major professor at MIT, just didn't have enough computing time. And he also complained that programming was hard. He said, what we need is a good handbook of how to compute. And he was convinced that this group was the one to do it, and talked to both Abramovitz and Stegan, largely through Blanche's recommendation. They put together the proposal, and right after doing it, Abramovitz decides on a hot July day that it's a good day to mow his lawn in suburban Washington, and has a heart attack and dies. Irene Stegan finishes the work. And if you go through the book chapter by chapter, each chapter is contributed by a different individual. Almost all of them originally started as human computers with the WPA. Gertrude Blanche is in there. Arnold Lowen is in there. Abramovitz and Stegan. There are a few others who are not. There's Frank Oliver, who got his start as a computer in England because he's English. And there are a few Cornelius Lanchos who never were computers, although they worked with them. But it is, in fact, their finest hour, the one thing that they have left as a legacy. Gertrude Blanche gets a little more of a legacy. She is retired by LBJ. You may recognize the tall guy there. Gertrude Blanche, I feel in getting to know her through her letters and her diaries and her journals, was a woman of great integrity in everything except how tall she was. She claimed to be 5 foot tall. It is a complete lie. She's about 4'10". But this is the end of her career. She ends up becoming a mathematician for the Air Force and serving in Dayton, Ohio at the Aerospace Research Laboratories. Her feeling about electronic computers, I think, is summarized here. The story of the human computer, in many ways, is the Pinocchio story. It's the story of hoping against hope that this work will make you a real scientist, will make you a real person. None of them had any major contributions to the development of the machines, although some served as models. George Stibitz used his computing staff as models. The Math Tables Project was modeled by other organizations, including the Manhattan Project, including some of the early computer designers went to see how they worked. The human computers thought that they were going to get in charge of them, that they would move these machines into their offices and things would get easier. And I've actually learned today, in some cases, that was actually true. At Ames, there is some truth to that claim. But for the most part, they were replaced. And when they were replaced, they went off to do things that had nothing to do with computing. They often would harass local school boards about why math education wasn't good enough. Or they would write letters to the editor of the Times, finding mistakes in calculations in various places. Step by step, they retired. As I see it, they probably were active as a group, doing hand calculation. Some may be into the 70s. Certainly they were active in the 60s. But it was a legacy that as they dropped aside, their families didn't know how to ask the right questions, or they knew vaguely that they had done something important, or that somehow in the course of their lives that they were connected to some scientific work but didn't know exactly what. Gertrude Blanche's family, for example, knew that she had done work for the Manhattan Project but wasn't quite clear on what that meant, and really didn't understand the work that she had done with the Math Tables Project and the other human computers. As I sort of started going through this process and tracing it back and tracing the growth, that's largely what I encountered. People saying, I didn't know, I didn't understand. When I found people who were still alive, and there have not been many that I have found from the Math Tables Project, it was always, we didn't do much. It wasn't much it wasn't something you would understand. But as I got probing with it, there was this wonderfully rich history of what predated the computer, of the work that was done to lay the groundwork. On February 14th, 1946, when we announced that we had the ENIAC, we just didn't say, hey, we've got it, what can we do with it? It was doing a bunch of work that was done by hand, by people like Gertrude Blanche. And of course, the one thing that to me that paces it all through is Halleys Comet. We have to get back there, don't we? Halleys Comet came back in 1835, 1910, and of course, 1986. Each time the calculations were done more quickly, each time they were more accurate. In In 1835, it was done by a small group of French mathematicians again. They got it down from 30 days accuracy down to about 2 weeks. They knew about Uranus then, and they were just better at computing. 1910, they really had the modern notion of how you solve a differential equation. They knew about Neptune, which was useful. They got it down to about 2.5 days. For the 1986, it was done on a UNIVAC computer in the 1970s using Fortran. Of course, by the time the Comet arrived, we had PCs, we had Sun workstations, we had Mathematica. And we had all sorts of things that could have made it a lot more accurate. But in the decade that progressed, no further work had been done, and so we had it down to about 2.5 hours. My feeling is when it comes back, which is in 2066, which we are all looking forward to, I know, everyone in this room, our grandchildren, looking over our college transcripts while they see this comet, are going to look at it and say, you know, we've got this down to what, 2.5 seconds, 2.5 milliseconds, nanoseconds, I have no idea. They're going to get it darn accurate, and they're going to use it using methods and tools that we do not know of. And they're going to think it's quaint that we used to have this thing called a spreadsheet or a Palm Pilot, or that we took a course called calculus. And I wonder how many of them are going to wonder that it was once done by hand, by a group of men and women who called themselves computers. Can I end up with one last thing? I've been talking with human computers today. This is, I'm choking on names. Ruthwick. And can I read the thing over here? Marcy Smith, who are over here, and I have a group of the Ames computers here. I just would like to introduce you. I think it's very important to introduce because if we don't, these names will be forgotten. And it's not right, and they deserve the credit. We have Marcy Smith. Would you like to stand? I know you would stand. Marcy would stand. I had a wonderful time with her. And keep standing. We're going to get you all up. Marcy, we need to see some strength. Stand up here, please. Ruth is going to join you, and she would like to have someone standing with her. No, you guys, Ruth, would you please stand as well? We have Jessie Gaspar. Yes, Jessie, who I met earlier. Claire Bergrum, who is right here. Enid Pate, right here next to it. And Mary Anderson is our last. I'm so glad you came here tonight. I feel privileged to be in your company and just so grateful for the work you did. And supposedly now I get to take questions, I think. Let's give it a try and see what happens. The empirical method.
Yes. You were, in your flow chart, you were referring to planners. And today, I guess the analogy would be software engineers.
Probably something, yes.
Yes, and then the computers, of course, back then were humans, but nowadays we know they're machines.
Yeah.
Well, what do you anticipate happening in the future? Do you anticipate that these computers will be an actual cross-section of human and machine together?
You're asking a hard question of me. The question was, what do I see about the future? We had the planners who are like software engineers or programmers, and we have the computers which are now machines, and what do I see happening in the future? I suppose this is where I can beg off and say that I'm a historian and I like to look backwards. I think, in answer to your question, I think you see things clearly. My work on this is that has sort of taught me that the vision precedes the technology. That we have something we want to do, and we try to do it very hard until we eventually figure it out. In particular, there's one of Gertrude Blanche's assistants was a woman who ended up working for UNIVAC, and she gave a paper in 1953 that said, "Let me tell you something. In the year 2000, we're going to have computers that sit on your desk." And they're all going to be connected, and they'll have graphics and pictures. And you read this thing, and you say, my goodness, how did this woman see so clearly? And then you turn the page, and then she tells you how it's going to happen. And she misses the technology by a mile. It isn't even close. She describes these banks of cards, because cards will be the cheapest storage in the future, and we'll make them very small. We'll have these teeny cards with 80 columns on them. They're the size of postage stamps. And there'll be these machines shuffling them around, and they'll be running through conveyor belts. It's a lovely article. The vision she had, and the vision she probably got in discussion with others in popular fiction of the time, but the technology, she had no idea. So I'm going to beg off on the technology. I know that there are people who are fascinated with the idea of merging the power of machines and mechanical memory with human consciousness. And my guess is that somebody's going to make that happen. I have no idea how. Does that answer the question, or does that help?
That answers the question. That's actually, I was thinking in terms of genetics and biogenetics and like nanotechnology.
Mm-hmm. And
nanotechnology wants to go very minuscule and get down to the unseeable, the size smaller than an atom.
Yes.
And I was wondering if you see any kind of future with nanotechnology converging with humans to produce an evolutionary species that's part machine.
You're asking a hard subject of someone who looks backwards. I believe in doing long division by hand. I think you're outlining issues that are there and that very clever people will do clever things with it. I have no idea. But it's a good question. It's issues we must follow.
Thank you.
Thank you.
Thanks so much.
Yeah,
Yes.
don't worry, you're going to hear me. So, two things. One, and these are both looking backwards. Luckily,
Oh, good, good. I like that. Much better looking backwards.
One is just day to day. I mean, how do you know somebody, 9 calculations back didn't make a mistake? Like, how do they do things to kind of actually make sure this all works? And the other thing was, when did slide rules come along, and were they accurate enough that they could play a part in this? Or?
Okay, can I answer that one first and go back to the other? Slide rules are, of course, invented with logarithms. They become mass-produced in the middle part of the 19th century when we have machines that can cut those grooves. And they become part of the engineering curriculum, about 1885, roughly. They're, as I'm sure many people here know, not that accurate. And one of the interesting phrases that I didn't know before I started this project is when we use the adjective astronomical, we're using it to refer to accuracy. We usually sort of mean that that's outrageous or that's, astronomically big. It got that way by meaning astronomically accurate, calculated to 10 to 15 digits of accuracy. Slide rules can do 2 on a good day with a fair wind. Most human computers did not use them. They used either books of tables. Once the adding machine came in, that was heavily used. I've learned today that Frieden calculators were heavily used by the late 40s and 50s. But the big thing that made a difference was high precision adding machines that could carry 10 to 15 digits. So I have not done much with slide rules. Those of you who have the book, you'll see it's a very thin chapter, extremely thin. Accuracy is an interesting problem. And it's an interesting problem that dates back to the very beginning, and they're aware that there are multiple sources of it. Babbage has several wonderful essays about how you think you just have 2 people doing the same calculations, and you can compare and you'll find mistakes. And he did some studies that suggested people working independently tend to produce the same errors, or do so far more regularly than you would like. People started developing ways of taking apart calculations to double check it. The common one was called differencing. It worked very well with differential equations, with tables, with other things, where you take adjacent numbers and you take their difference, and then you take differences of differences and then differences of differences of differences. And there are certain patterns that you would look for. And in those patterns, you would begin to identify, and in some cases be able to correct an error just from those differences. From that, people put together other functional ways, and by the late 19th century, checking on that kind of calculation for errors is taking apart numbers. The problem that always remained, other than that, there are 2 major problems. Solving differential equations and doing linear algebra. Linear algebra was a lot harder because it was much more difficult to get intermediate things that you could check. You sort of were leaping off with faith, and you might be able to check it at the end, and then it might have been 6 weeks ago you made the mistake. Hence, it was a problem that tended to be done by very skilled people and was not passed off to unskilled. And they worked very hard to find intermediate ways of checking. That was a hard problem and remained hard until the electronic computer. In fact, there's a group of people I talked with who joked that the electronic computer was invented to do numerical algebra and nothing else. That's the only reason it was there.
Okay, thanks.
And thank you.
Yeah, do you have some comments on Richardson and his work with weather prediction?
Oh, I love Richardson, yes.
Yeah. And my other question was about like John Mauchly's wife, who I believe was a computer at Aberdeen. So, yeah.
That's another important thing. Yes, John, I have both a John Mauchly story. I did not pay this man to ask this. In fact, when he approached the microphone, I sort of quivered instead. Richardson. Richardson was a meteorologist, which is a tough stretch. He's a natural scientist in England during the First World War. Pacifist. When the war broke out, he decided he could serve by serving in the Red Cross. And to pass the time between battles, he worked out the differential equations for the weather, for numerical weather prediction, a problem that became one of the major problems for the electronic computer in the 1950s. And the basic problem then is now is you divide the Earth into a grid, and you have several layers of atmosphere, and you can push you can set up differential equations that follow the movement of the atmosphere, the heating and cooling by the sun, the changes of humidity and air pressure. And the equations are not that hard. It's just that there are a lot of them. And Richardson, in spending his time on the Western Front, looked out on these trenches. And he writes also of running his ambulance up and down and picking up the war dead in the morning after the battles. And he wondered if these trenches could be put to better use, or the men in them could be put to better use. Because as he was doing, he decided if you divided the world into about a globe of about 2,000 grid points, which would put, for example, LA and San Francisco more or less in the same grid point. So that kind of makes you worry about the weather prediction. Or New York and Washington. That he calculated that for each grid point, he would need 32 people to do the calculations to keep pace with the weather. To compute a 3-hour change of the weather, they would have to compute for 3 hours. So running it up, he figured he needed 64,000 people to keep pace with the weather, or probably double that to get ahead of it and make a true prediction. And he described this wonderful computing room that's basically a giant stadium, domed stadium, where people are, the dome is the inside of the globe, and people sit in chairs in front of the part of the world they're computing, and papers are being passed around, and they have little lit signs that show the temperature and humidity. It's in the center. And it has this wonderful vision of it's led by a senior scientist who stands at a center podium like he's conducting. And he has red and blue lights to shine on people to tell them to slow up or slow down or speed up. And what's interesting to me is really his final comment. He describes this as located in this wonderful Arcadia with good weather and with lakes and trees and playgrounds for those that spend their days computing the weather deserve the right to live in its blessings. It's a wonderful thing. His problem and his equations, not exactly as he wrote it, but with little change, becomes one of the major tasks for John von Neumann's computer at the Institute for Advanced Study, and remained one of my first jobs was working on the Burroughs Scientific Processor, which was, as we told ourselves, going to produce the really first good usable numeric weather forecasts. We never quite got the machine working. The Cray did a better job anyway. But that's the first one. It's a lovely, I think, piece of visionary work that, like the first question, technology eventually caught up with it. The second one was Mauchly. Mauchly gets into the ENIAC because of an interesting calculation. The Math Tables project was not the only work relief computing room. There were 2 others with the WPA, neither of any import. However, the ones that are of interesting and of import were sponsored by another group called the National Youth Administration. The National Youth Administration was the work relief program for the middle class. It basically kept kids in school. It provided jobs to universities and colleges to keep students from having to drop out and support their families. It was highly controversial, as all WPA, all New Deal was. Most colleges sort of took the money as if it was diseased or spreading disease. Several schools refused to take it. Columbia refused to take it. The most active National Youth Administration group was at Indiana University, which got a very large grant. And the person there, a man named Harold Thayer Davis, no relation to Charles Henry Davis. Those of you who have my book will notice there are a lot of people named Davis. As far as I know, none of them are related. He produced 3 books called something like Handbook of Mathematical Functions, and I don't quite have the name, but it's a book of tables on specific higher order mathematical functions, 3 volumes. Mauchly also got money to form a computing group. And computing groups were very common because you could employ a lot of people, no one really asked what you were doing, and people had problems. And Mauchly had a friend at Ursinius College who was interested in weather and interested in studying it with correlation. It's a method of calculation, a method of weather analysis that was largely discredited about 50 years before. Karl Pearson actually tried at it and concluded that it just was far too cumbersome to work. But Mauchly and his colleague were interested in a specific narrow problem that seemed to have some promise. And Mauchly put together a computing group of about 12 people, which was the common size. Most of the computing groups were 8 to 15 people. They would have 1 or 2 planners. They would have a staff by the 30s of at least half women. And they would work together with adding machines. That was the common form. The Math Tables Project is a bit of an anomaly.
Except for the big domed room with the meteorological calculation going on in tandem, the image is that most of these calculations were of a single person doing a calculation of some function on a single argument, and each person was doing a different argument. Were there more complicated array or mesh computations done? And if so, what was the protocol for sharing information? What was the mechanism for doing that?
The common mechanism was almost all the computing was done with worksheets, which by the 1890s were mimeographed using the standard mimeograph stencils. And depending upon the organization and the problem, the idea of one person working on one problem with one variable is largely false. It's false by the end of the 19th century. The Math Tables Project is perhaps the most sophisticated, but it illustrates my example. It divided its computers by the 4 basic operations. This corner, or the largest corner, would be the addition group. Smaller group up front were subtraction, because a lot of the adders didn't get negative numbers. You're taking a bigger number from a smaller number. What does that do? And what happens when you take a bigger negative number from a smaller negative number? You know, that was not clear to them. And so they divided up. In this group, it was clear. Multiplying would have been over here, and they were small, and they would do a single number versus a large number. And way back there, we have the few, the small, the proud, the knowledgeable, the long dividers. And the worksheets would pass between the groups. And you'd take a worksheet and you'd say additions, 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 some subtractions. And you'd give them to the subtractors, and they would do all the subtractions on it. And they would say, oh, some multiplications, and pass it over there. The flow of paperwork determined it. There's a very famous example, Richard Feynman did it at Los Alamos, in which he is very proud of what he's done. And he is not telling you that he got it by visiting the Math Tables Project in New York City. You get that only by looking at the Math Tables Project log, where they set up a series of people with adding machines to follow the flow of the equation, and the paperwork went uniformly through. That you'd have one group of people doing some integration here, and then some people doing some addition and other work, and it would sort of go through this flow and come out the other end. Excuse me, my voice is starting to slip a little bit. Feynman did it in a test to compare it with an IBM tabulating machine, IBM 601 tabulating machine. And this group of computers did fairly well for about 3 days, and then the tabulating machine beat it. And that story, when Feynman told it and when others have retold it, have tended to say, see, computers were faster than humans. And I read it as saying, as late as 1945, humans were on a fair fight with what IBM could deliver. And in fact, if there was a lot of changing of programs and changing of ideas, people were probably ahead. And I think that's what Phil Morris was arguing. When people had the time, they would get at these worksheets so that they would go through a group in an orderly way. And that would be the way that would solve the problem. And that would be the way that would be most efficient. The one place where it was most clearly seen was in 1948, when a group of the Bureau of Standards does the first large-scale test of linear programming. Linear programming is linear algebra. It's a classic problem defined by George Stigler in 44, 45. You have 88 food groups, meet the minimum daily requirements, and have the least amount of money for your meals. And 25 people worked on it for 4 weeks, passing papers through the snake that basically as it went through the snake, it would do one row of elimination. And then they'd take all the paper and they'd stick it at the start and it would go snaking through again. They never used it. They just wanted to see how fast they could do it. And the reports, you turn over the report, which gives the results and how long it took them. And on the back, there are notes about how fast the ENIAC would have done it on the exact same operations. So that's the kind of process, and I hope that helps clarify it. That they did very much think about how to use people best, how to have paper circulate through, and it was this worksheet, this mimeographed worksheet, that allowed them to do this. You're an easy audience. Oh, I see one more. Hello.
I was actually going to ask a question about linear programming, and thank you very much for providing a segue to it. How much linear programming has been done in the industry, in not particularly computer science industry, but in actual business? These multiple variable equations.
Right. By hand or with machines?
Well, before machines. We kind of know more about machines. Not the stock market, but mostly fulfillment kind of equations. The war industries, these types of things.
Well, I'll give you a complicated answer that may not answer your question, but allow me to stall for time and show off how much I know.
That's what I hear.
Linear programming is developed right at the end of the war, and it's George Danzig, and it really comes into its own 44, 45, 46. There are no large-scale tests of it during the war. The first large-scale test is in April of 48. It's the one I mentioned. Prior to that, there's a fair amount of optimization technique that is sort of jerk things around and force it into position. There's a certain amount of trying to manipulate least squares to do the same sort of stuff, which is another big computing problem. Which, don't get me started on that. That gets me into Henry Wallace, and I love Henry Wallace. Henry Wallace is a Secretary of Agriculture who loves least squares. And, oh, he's nuts. It's not quite the same thing. It was much easier to do, but it did not produce optimal results and sometimes produced wrong results. That was fairly active through the 30s. In particular, the oil industry was starting to use it for their work, which becomes the big user of linear programming in the early 50s and is the major big-scale work that is done. The Bureau of Standards gets involved in developing linear programming programs in the late 40s and early 50s, and I believe those are the ones that get copied and tweaked around and pulled into the industry, and were largely the ones that did the early work. I don't think there is much human work on linear programming, although I think through the 50s, there is still a certain amount of these ad hoc least squares tweak around to close your eyes and hope this is the right result kind of work. In particular, the von Neumann Archives has a nice big fat file about linear programming in the oil industry. It's a half-inch thing. It's great stuff. And that leads me to believe that that's the first major commercial use of it.
Thank you very much.
Thank you. Whoops, he snuck up behind you. It was not malicious, though.
Hi. My impression of computing is that there are some people who are really, it's great for them, and other people, it might be stressful or boring or whatever. And I was wondering if there were a special, I look forward to talking to these computers
They will
later.
give you an idea, I think.
But what psychologically was done to keep people motivated and, excited and productive?
That's a very good question, and that also has roots that go back to the mid-19th century. Simon Newcomb ends up taking over the American Nautical Almanac in the 1870s. And his favorite computer is a person who he describes as accurate to a decimal point and having no worldly ambition at all. Alcoholism was a severe problem among human computers through the start of World War II, a very severe problem. This man with no worldly ambition was eventually fired for being an alcoholic, and many observatories had trouble with it. There were people who were suited to it who loved it. The Iowa State group was led by a woman named Mary Clem, who had nothing more than a high school education. And she got it because she was learning what the scientists around her were learning through her numbers. Those people seemed to be the most satisfied and who enjoyed it, who could engage it, and who worked in environments that would engage it. Ruth Wick to me talked today about how she would be taken down in the wind tunnels and show the tests and experiments that would connect the data that she was working on, which I seem to recall you said was somewhat dull and boring. Are you going to fess up in front of everyone? She will not fess up here. You'll have to look at the tape later. But it was a way of making the computing staff feel that they were part of it. And I think that was important. During World War II, many of the computing groups were not classified, and they were not allowed to see what problems they were done. And in particular, the Math Table Project in mid-44 gets something from a group called the Manhattan Engineering Project, and affixed to it is a big statement that says, you'll not show this paper to anyone, you will have no discussion of what units may be involved here. This paper will be destroyed, which they did not do, at the end of when you're done with the problem, and you will not inform the computers of where this comes from. It's clearly, if you look at the equation, it's the explosive lenses for the plutonium bomb. But they did everything they could to make sure that no one knew that. And I think they found that frustrating, ultimately. So it's bringing people in, a change of work, but nonetheless, they did find it boring and they did quit. There's the famous computing group at the University of Pennsylvania that led to the ENIAC, and there are a lot of reports that said, we were working so hard we didn't have enough computers. They didn't have enough computers because they trained women for 6 weeks in mathematics. They would work for 4, get bored, and find a better job. Their average time of turnover was very, very short. And so it was a very real problem. And it's a long answer for a short question. Oh, I see someone else coming up. I tell my students at times like this, if you're getting antsy, stand on your chair, say, this is nuts, storm out of the room and slam the door. Very few of them take me up on this. And I don't think it's for the quality of my lecturing.
So I would be interested in your opinion of the modern-day weather models, computer models.
You're asking a poor, humble person with just a degree in applied mathematics who looks backwards, not forwards. My sense of modern weather models was what I worked on in the 70s. And that's what I used to go evaluate when I did work on Richardson for the book. And I pulled out my own notes and I discovered that they were amazingly similar things. I have no real sense of what goes on in 2005, other than I think they've made the grid points smaller and they've added a few extra terms. Is there a numerical meteorologist expert in the house? Okay, then that's true, completely true. I suspect there's multiple processing and splitting apart and a lot more parallelism. I believe grid points are now down to the order of less than a mile, but I do not speak at all with that because that's what we were trying to get in the 70s. And as we know, other than being the highlight of American culture, that was some time ago. I'm sorry I can't answer you. I wish I could help more. There's no fate worse than being talked to death, and I would encourage you all to get now while you can. Well, then I'll turn to you.
Questions? Thank you very much.
Thank you.